VLSos here. This is a video lesson on converting an area question into sigma notation. And to present this, we're going to work with a specific example and then generalize it along the way. We could be asked to estimate the area under a function and be given that function on an interval like from 1 to 5 using 4 rectangles. Notice in this question it's chosen for us what method of estimate we're going to use, in this case rectangles, and 4 of them, which is crude, but good for an example because it's manageable. If we weren't told to use 4 rectangles, we might produce an estimate using trapezoids for more accuracy and use as many trapezoids as possible given the technology help that we have available. To get a visual on this, the interval from 1 to 5 and this is a parent quadratic. So if we put 5 into the function, we would get an area 25. To use this space, it might look like this. If we're going to use 4 rectangles, we could choose left, rights, or mids. For the purpose of this example, I'm going to choose left rectangles. And here we have 4 rectangles, and their heights are determined by function values on the left side of the rectangle. In function notation, this language could be expressed as capital A for area, and then in the function parameters, in parentheses, we would supply the expression for the function that we're using with a comma and then a double inequality to identify the interval, and then we might have to be told outside the parentheses that we wish to use 4 shapes, 4 rectangles. So n, the number of shapes that we're going to use in our estimate, is equal to 4. In general, this is the function of x, and typically we use a and b to represent the beginning and end, or the lower bound and the upper bound of the interval. Now this is the question, but how do we answer it? Because we have even intervals for the bases of the rectangles, then we can utilize the concept of delta x because it's uniform. It's the same change. Delta x, the change, can be observed to be 1, but we calculate that as the latter value in the interval minus the former value, or the endpoint minus the beginning, divided by the number of rectangles to get, in this case, 4 divided by 4 is 1. Delta x is 1 in this example. In general, that is the b value minus the a value divided by n. Sigma notation requires an integer index. K is often the indexing variable that we choose, sometimes j. And we're going to begin our index at an interval at the lower bound of 0. And then in this example, if we were to start at 0, we would count up from 1, 2 to 3 and finish at 3 so that we get 4 integers to produce the 4 rectangle areas that we're going to sum together. And the argument for sigma is the formula for the area of the shape that we're going to use, which is a rectangle, and the area of a rectangle is base times height. The base in this case is delta x, or 1, and the height is the function, but not with the variable x. We need to transform the x to use the k values. And the k values are integers that begin with the first value at the location A, or in this case 1, and then increase by delta x's for every value of k. Or that is delta x, which is 1, times k. This is the new input for our function, and our function is squaring. So if we have this input, I square it afterwards to determine the height at every location. And then when we multiply these, we get the rectangle areas. And then when we do that for every integer in the index, we get all of the rectangle areas, and we add them all up to produce the estimate. In general, it's good to start a left-hand estimate with an indexing variable of 0. And if we do, we always go up to 1 less than the number of rectangles that we're going to use. The base is delta x. And the height that we multiply the base by is always the function, but not composed with x, composed with that beginning of the interval a plus delta x's for every value of the index k. And this is often the general form of sigma for the left-hand estimate using rectangles. We could translate this into a right-hand estimate with the same argument. The base is delta x. The heights of the rectangles are the value of the function composed with a plus delta xk. But the index is changed, so we start at a k value of 1, which is effectively 1 delta x away from the beginning, and goes up, so we have an upper bound that is equal to the number of rectangles that we're going to use, n. Now, if we're going to use the trapezoid to be the shape under the curve for better accuracy, then the formula in the argument wouldn't be the formula for the area of a rectangle, it would be the formula for the area of a trapezoid. But it would still use the values of delta x and function values at the locations that are needed for the equation for the area of the trapezoid.